Hello everybody and welcome to the NPTEL online course on microelectronics devices to circuit. This module is dedicated to the fabrication procedure for a ordinary silicon based design. So, what we will be looking into in this module is if you want to manufacture IC or integrated circuits on silicon, then what are the steps which you should do. In our previous discussion we have discussed already about in details about bipolar junction transistors and metal oxide semiconductor field effect transistors, and we have also seen what are its possible usage in both digital and analog domain. We will be taking up MOS as an amplifier in our subsequent modules. Typically as the course is progressing, you might be seeing that I am giving you a flavor of both digital as well as analog electronics, right. Subsequent few modules will be devoted for analog, and then during the later courses or later sections of these modules we will be actually moving to, when we go to week 10, 11 and 12, we will be actually looking into digital applications of these MOS devices. So, this gives you a full breadth of design flow as far as silicon MOS device is concerned. Now, we have already looked into those basic facts. Now, let me give you a basic idea about the basic fabrication steps which is available with us typically in a design. Now, the outline of the talk therefore will be, we will look into the basics of fabrication, right. We have looked into the basics of fabrication. We will actually look into the various concepts or various meaning of what is the meaning of silicon wafer, what are the limitations of silicon wafer. We will be also looking into a very important term known as photolithography, which actually determines the channel length or the dimension of the devices. So, that is photolithography we will be looking into. We will be looking into diffusion and ion implantation. These are primarily meant for doping and then this doping, if we want to change the doping or we want to alter the doping, then we use diffusion or ion implantation systems. Then for example, if you want to do a metallization, for example you want to grow a metal, then you require to do a deposition, or even maybe a simple silicon dioxide growth over silicon will require a deposition. We require etching because etching will help us to remove the areas where you want to grow metallization, and then planarization means making it plane by doing polishing. We will be therefore then going into the inverter cross sectional view from the fabrication point of view, and then finally we will look into the various fabrication steps in this design, right. So, that is a typical outflow for this outline for this design for this module. Let me see what is the silicon fabrication. So, most of the time as you can see, CMOS transistors are fabricated on silicon wafer, right. There are few reasons for that. Silicon, for two reasons. Silicon is, first of all, if you go back very clearly, silicon, if you look very carefully, then you will understand that silicon is very economical in nature, right. It is very economical. So, that is the reason we use silicon. So, reasons for using silicon, if you want to use reasons for silicon, it is pretty economical, right. And the second is ease of formation of native oxide. So, if you leave even a simple silicon wafer here, it mixes with oxygen to form silicon dioxide, right. So, this is what you get, silicon plus silicon dioxide, which means the silicon automatically does a double bonding with O and forms silicon dioxide. So, formation of native oxide is very easy. So, if you want to grow a MOS, this MOSOS, which is oxide and silicon, is a very natural growth, right. So, that is the reason we use silicon for all practical purposes, right. The cost we pay for it is, for example, we cannot use silicon for optical domain, right, and that is the problem area of silicon. Then you have to go for 3-5 semiconductors, but for the time being we will be concentrating on silicon itself. Now, lithography, as I discussed with you, is just like a printing press. So, what you do is you have a sort of a silicon wafer over which you want to write something by using certain techniques, that is known as lithography. Every lithographical steps will have different material. For example, if I want to grow interconnects, then I will using copper in the lithographic techniques. If I want to grow, for example, just the contact, maybe I will be using something else, maybe I will be using aluminum to do that, and so on and so forth. So, depending upon the usage of those photolithographic lithographic techniques, you generally have photolithography and electron e-beam lithography, or direct e-beam writing also is there, but these two are the most important ones. Photolithography, as the name suggests, is very simple. If you go back to your basic photography, right, when you do a negative, what you do is that you do have a negative and you let the aperture open for a small duration of time, light flows in, right, wherever there is a human being or a structure outside, the reflectivity is low. As a result, the chemical within that negative gets reacted less slowly, and other parts gets more reacted, and therefore, when you make a positive one, you automatically get the image. Exactly the same thing happens in silicon as well. So, photolithography is an important step. On each step we use different devices. Now, the starting material is basically what is known as a silicon wafer, right. There are two types of silicon available to us. One is known as MSG, which is known as MGS, sorry, let me grab it for you. It is basically your right, it is basically metallic grade silicon. So, it is metallic grade silicon. You also have an electronic grade silicon. So, this is basically your electronic right grade silicon, and this is your metallic grade silicon. So, as you can appreciate, this is much more purer. So, this is much more pure as compared to metallic grade. So, typically when you fabricate silicon wafer, you first fabricate MGS and then you do more refining to get EGS. So, in EGS you will have very low impurity, very low impurity, both in terms of external agents or external agents, as well as the crystal itself. The crystal itself will be so even that you will not be able to distinguish between a bad crystal and a good crystal, right. Typical diameter is from generally 4, 12. So, we typically have diameters of 4, 8 and 12 inches, right. So, these are fixed. You cannot have more than these diameters of silicon, because there are certain fundamental problem areas. If you go beyond this particular diameter, you will not be able to stabilize the system, and moreover there will be large amount of defects inserted within the silicon if the diameter of the silicon grows too large, right. Okay. So, this is the photograph which you see here is basically that of a wafer, with the wafer has been cut into smaller parts. So, each one of them is basically a silicon chip here, and you can actually start doing wafering there. This is the final form of wafer which you see, where you are actually doing the layout and doing the designing. With this knowledge, let me come to the photolithography. The photolithography transfers selective pattern from a mask to photosensitive layer, right. So, I have a mask. So, if you, for example, if you have a mask, right, and your mask is an open mask here like this, then light can filter through this mask here and fall onto maybe a photosensitive layer. So, this is my photosensitive layer, right. When it falls, there is some chemical reaction. The first reaction is basically your oxidation layering, right. Typical photography step is that it is an optional step. Why? Because you do not want the wafer to go bad. So, what people do is that let a small width of silicon dioxide grow over silicon. So, a small layer of silicon dioxide is growth over the silicon, right, over the complete wafer. When you do a resistive coating, then what you do is that a light sensitive polymer, photosensitive polymer, which is soluble in an organic solvent or an agent, and you put a layer of that over this silicon dioxide, right. It can be positive, it can be negative as well. Positive basically means you can drive it out and let the material remain there, and negative means let the material come out and let the other part be there. Now, your third point is basically my stepper exposure. So, you do have a glass mask over which you have imprinted the pattern by which you want to photolithography. You put it over the wafer, and then both mask and wafer are exposed to ultraviolet light. So, when the UV light falls, wherever there is a mask and there is a transparency, the UV light will fall on the silicon and will expose it, whereas those areas where you do not want it to expose, it will remain fixed like this. Then the wafer is developed into acid or base solution to remove unwanted photoresist. So, whenever unwanted photoresist will be there, you just remove it via chemical etching, and then soft bake to harden the remaining photoresist. So, the remaining photoresist will be what will be useful to you. So, what you do is a soft bake. Soft bake means that you do it at very low temperatures and automatically only those photoresists remain there, right. Acid etching basically means that once you have actually done all these things and remove unwanted photoresist and you have hard baked your photoresist which you want, or the required photoresist, then you do acid etching. What is acid etching? You uncover by using acid or base, you do the partial removal of the uncovered material, right, so that you do not end up having spots in your wafers. Then you do what? You clean the wafer with a deionized water, distilled water, also referred to as DI water, and dry it with nitrogen, right. So, we get the wafer with us in a detailed fashion. Now, let me do a diffusion and ion implantation. Well, diffusion as the name suggests is basically for purpose of generally for the purpose of inserting dopant species, and as the name suggests, what does doping do? It carries species from a region of high concentration to a region of very low concentration, and as a result what happens is that there will be a diffusion species between point A and point B, depending upon the concentration gradient as well as on the diffusion constant of that particular material. The material will either sit deep inside the original species, or if it is not, it will sit much ahead of it, right. So, as I discussed with you, dopant, so typically the wafer is placed in a quartz tube because it is quite pure and you do not have any reaction from the quartz, and it is heated in a furnace with 900 to 1000 degrees centigrade. So, when you heat it, it becomes more reactive in nature, right, and therefore, you allow the dopant species to diffuse through the exposed surface. Of course, as you can understand, the diffused species dopant concentration will be highest at the surface, and as you go inside the surface, percentage of the dopant species starts to fall down, right. And this is a standard problem area which people face in while doing doping, is that the doping is always highest on the surface and goes on reducing as you move within the surface, right, and therefore, the doping concentration is highest on the surface. Please understand, diffusion is again temperature dependent phenomena, right. So, on chip temperature what you do, which is basically my heated furnace, will determine the most optimal value or the procedure for fast movement of ions, right, fast movement of dopant ions in this case through using diffusion. So, it is very critical to set your temperature of the quartz the quartz tube in such a manner that it is the most optimized one. So, for example, if you keep it very largely heated up, the chances are the dopant species move so fast that it might not sit even in the silicon because the energy is very high. Similarly, if the gradient is very small, then it will not be moving from point A to point B by virtue of diffusion, right, and that is you should be very careful about as far as diffusing and ion implantation is concerned. Let us look at ion implantation. What is ion implantation? Ion implantation is bombardment of dopant ion using an accelerator. So, you should have a good accelerator. This process provides an excellent dopant control, right, and complex doping profiles can be made using multiple energy implants. Say you want to first of all make something like this, right, and then you want to make something like this. This is the dopant profile. You can easily do using ion implantation machine, right. For example, if you want to make a profile something like this, so peaked, right, then use a Gaussian profile and make your FWHM full width at half maxima as low as possible, and keep your D as large as possible, dopant species as large as possible. So, within a short domain, since your FWHM is full width at half maxima, right, FWHM, if I want to point out FWHM, this is basically full width at half maxima, which means that if I plot using a maybe a Gaussian surface, then we try to find out the maximum value, which is this one x. We draw a graph which is from x by 2, this is x by 2, and then we check the values of the dopant species here, and then we say that this is my FWHM, FHM, fine. So, this is full width at half maxima, right. So, when you get full width at half maxima, it tells me. So, now if you want that the profiling should be peak, or you should have a peak profile, keep your FWHM small and you can actually get a peak profile. Similarly, if you do not want a peak profile, you want a wide profile, then it is also advisable to keep it wide profile and you get something like this. So, depending upon the type of dopant species you are using and the type of temperature which you are using, you can actually have either a like you can either have a proper control over the channel ion implantation and other channel wise, right. So, but the problem with this ion implantation is that the energy is so high, right, the energy is so high that you end up having maybe dislocation of the atom itself through which these charged particles are passing, right, and that is a problem area which people face. Let me come to deposition. Well, deposition is conducting layers such as polysilicon and aluminum, and insulation and protection layers are silicon dioxide and silicon nitride, and they are done by CVD process at high temperature chambers. So, I have a high temperature chamber, right, and once I have I do a CVD, which is chemical vapor deposition, and I deposit layers of silicon dioxide and nitride, which are both by the way dielectric in nature, over this area. So, once you have actually the material and then you have been covering it with the material across the board, then what you do is that depending upon the pattern where you want the photolithography to work, you start to remove, if you are doing a positive photolithography, start to remove those areas or etch those areas through which you want the light to go inside, right, and then you do that easily using any of the dry etching or wet etching, right. So, chemical in case of wet etching, we use a chemical solution to etch away at a given temperature, whereas what is the dry etching, chemical reaction occurred between the material and gases and the product will be the gases itself, right. So, seldom people use dry etching, most of them people use wet etching, and that is the reason why, and that is the reason for this wet etching is that it is relatively simple, but the cost you pay for it is that you are not very accurate in terms of appropriate etching, right. What do you mean by planarization? It is basically meaning mechanical planarization, and is used to fabricate any metal layer to remove excess material and to planarize the surface, right. So, what people do is that they have a planarization technique by which excess layer is removed first of all, and after the removal excess layer, what you try to do is that you try to have the model layer perfectly plane in dimension. So, let me see the inverter cross section view. As you can see, this is basically a twin tub process, and in the twin tub process I have p type substrate. This will act as the substrate for NMOS. However, you need to grow an N well within the p substrate for a p type substrate to be formed here, right. So, for a p type substrate to be formed here, you require if you want to have a PMOS transistor, try to make this one. So, this is basically your N well, and you try to make within the well another well which is basically N well, and from there you can get the value of your p type material. Similarly, the p substrate itself acts as substrate to the MOS transistor, which is basically your N type, and therefore, this is your N type substrate which you get. So, I have an N type and p type, they are separated by this metal 1, right. So, this metal 1 is separating the two, and from here and here and here you take the output value of the voltages or currents, right. Okay, let me look at the well and substrate tabs. So, I have a well tab which is basically my the well tab and substrate tab. If you look very carefully, this is my ground tab, right, this is my ground tab. These two are the tabs where you put an input, right, because this is gate to source, this is also gate to source, and therefore, I would expect to see these to be latched together, and this is the value of VDD which you choose, and here is another well available with you, right. So, these are the few N well process which is typically there with us. Any transistor or mask, any substrate must be sited to the ground. So, if I have p type substrate, that must be tied to the ground, right. So, I have a p type substrate always tied to the ground, and N well is always tied to VDD, means N type devices are always tied to higher value of voltage, and p type devices are always tied to a lower value of voltage, right. and use heavily doped well and substrate contact taps. So, if you use very heavily doped wells and also use substrate contacts, your effect of N will be reduced drastically in a device, right. Now, you have to create moreover you have to create a low resistance contact between substrate and the supply line. Otherwise, if you do not do that, there will be excessive voltage loss across the supply line, and therefore effective voltage available to you for running the MOS device will be relatively small, right, and that is the problem area. Now, let me come to the inverter mask set, right. We have got transistors and wires are defined by masks. So, these are basically the mask which is available with you, and inverter can be obtained by using 6 masks: N well, polysilicon, N plus, P plus diffusion contact and metal contact in metal. So, it is 1, 2, 3, 4, 5 and 6. So, you require 6 masks in order to do it, right, and these 6 masks can be easily purchased and can be used. But when you use these masks for fabrication purposes, the fabricator will come to you and ask you to change this mask according to his fab lab, right, according to his fab. So, please be careful that just by saying that you have been able to generate the fabrication mask means that you have done everything. No, fabrication mask as well as its final utilization is quite important as far as inverter mask is concerned. Let me give you a brief idea, there is nothing to worry about, you need not to worry, you have to just learn. For N well, this is the mask which you see in front of you. For polysilicon, it is this thing, right. For N plus diffusion, we have N plus diffusion shown by red. This is for P plus diffusion, right, P plus, and this is the contact which is given by black one, right. So, if you look at this point, metal is this and this are metal, right, and this is also metal which is available with us, and it is connected in series like this, right. Let me start off with a blank wafer and let me enumerate the fabrication steps which are there. We start with the blank wafer, build inverter from bottom top. First step is to form an N well, cover wafer with protective silicon dioxide, we discussed this point, right, sorry, with silicon dioxide. Remove layer where N well should be built, I think that is clear why N well should be built. So, remove the layer where you want to remove, where you plan to have N well, and implant or diffuse dopant into the exposed wafer, right. So, that you appropriately change it to N type or P type, and then strip off silicon dioxide. So, you have a silicon dioxide initially present, over that you do form N well, and after the formation of N well you try to do a protective covering of silicon dioxide, remove it and remove it and try to do your implantation or diffusion using dopant species which are basically your non-silicon dioxide based, right, and then if you are using silicon dioxide based, strip off the silicon dioxide and throw it outside. Now, oxidation is you have to grow at silicon dioxide on top of silicon, and the temperature range is basically 600 to 1200 degrees centigrade, right. With H2 and O2 is basically the reason you are putting it is acts as catalyst, right. They act as catalyst means they themselves do not part in the reaction, but they hasten the speed of the reaction in a much more detailed manner. So, we use oxidation for doing all these things, and it is done at 900 to 1200 degrees centigrade. So, what is a photoresist? Photoresist, as I discussed with you, is a polymer photosensitive material in which if the photons fall, it becomes sensitive to input voltages, and there is a problem. As I discussed with you, photoresist is a high sensitive organic polymer. For example, there are many organic polymers available, and one of the example happens to be photoresist. Now, so when you are exposed to light, it softens, the photoresist itself softens when the light is exposed to it. So, as you can see here, I have the native P type substrate. What do you mean? I do something like this, which means that I try to make this internal one as to be as silicon dioxide, maybe P type. So, what we get from here is that you get Na to be Np to be equals to say you had 16 plus, and suppose you had 16 and now you have 6, 16 plus 6 will be 22 per centimeter cube, right. Whereas, if you have metal layer you will have already 20. So, 20 plus large number 26 will give 46 per centimeter cube. So, you can see same technology you get a larger doping profile as compared to the previous case. So, let me move to lithography. You need to expose the photoresist through an N-well mask, right, and then sign off strip off the exposed photoresist. Once you do that, you are stripping off your all other things. So, what you do is that this is basically your the photoresist which you have fallen onto this bank, and as a result you strip out the photoresist from this directly, right. What is etching? Etching means that you etch the oxide with HF. So, I have an oxide formation taking place, I want to remove it for whatever reasons. Then what I do is I put HF or hydrofluoric acid, and that strikes off that metal layer, and there is and makes it almost non-existent. HF actually attacks the oxide layer where there is no where the resist has been exposed, right. So, wherever the resist has been exposed, this HF will try to attack those the exposed part in order to reduce the value of your reduce the attacks, right, parasitic attacks or otherwise. Let me come to the strip photoresist. Like as we are discussing it, we strip off the excess photoresist. We generally use in this case so we have a strip photoresist, which is basically what you do is that you remove the strip photoresist from here, and the remaining part is what is there, right. So, the reason we strip off is that we do not want the other part to melt away, right. So, in the next step when we do, we do not have to melt away the photoresist, and therefore we strip off the remaining photoresist. So, this is what we have stripped off. So, I have a silicon dioxide layer here, and I have a p type substrate over which I am doing the photoresist, right. We come to the N-well formation. Now, N-well basically meaning that you are doping with either N type dopant concentration, which is basically either phosphorus or arsenic, right. This is a group 5 element which you are doping with, and what you do is that this N-well is formed with diffusion or ion implantation, right. So, typically in most of the organization or fabrication techniques we use diffusion, right. What we try to do is that the phosphorus and arsenic are kept in a chamber at elevated temperatures, and then and this material is kept at a lower temperature relatively. So, there is a temperature gradient, and there is also a dopant gradient which results in the atoms of these phosphorus and arsenic coming towards and sitting at these positions, right, and you do have diffusion. You can control the speed of the diffusion by changing the temperature, also by changing the dopant species. You can also change the amount of dopant species by increasing or decreasing the dose in the ion implantation machine. So, the diffusion, if you look, we use arsenic gas in a furnace, right. What we do is that the arsenic gas is there, and we heat it, and arsenic atoms diffuse into the exposed silicon. So, the arsenic atom will diffuse and sit, these arsenic atoms will diffuse from maybe a this thing a glass, and from there the arsenic atom will be coming and sitting onto the silicon wafer, which is this the silicon wafer which you see, right, and the silicon dioxide, right. In ion implantation we try to do blast with arsenic atoms. So, arsenic ions are there, since you are accelerating, you require the particle to be charged, and therefore you have to first ionize your arsenic or phosphorus atom. So, when you ionize your phosphorus or arsenic atom, then you through an electric and magnetic field you try to push it, and a large dose of that charged particle falls onto the material, and as I discussed with you earlier, I can change the dose as well as the doping concentration directly. Now, so now you can understand why this silicon dioxide is important. This silicon dioxide is important because then this silicon dioxide does not allow for these arsenic or phosphorus atom to enter in these regions. So, this region is devoid of those group 5 material, whereas this region is having large amount of group 5 material, and therefore it is basically your N type well is formed, right. Now, we come to the N well. We using HF or hydrofluoric acid, we strip off the remaining oxide, right. So, whatever oxide layer was here at this point and at this point, we just use HF to remove it. Then therefore, now what we have is the bare silicon wafer, which is this one, and we also have the N well which is kept here, right, and then we will be using the similar steps later on. After this we grow a layer of polysilicon. This layer is known as polysilicon, right. We deposit a very thin layer of gate oxide, which is, so this is basically a thin layer of gate oxide which you see here. This is a thin layer of gate oxide, right. It is approximately 20 angstrom, which means approximately 6 to 7 atomic thickness available to me. Then you have then after this, after you have grown the gate oxide, which is basically a native growth, you allow for CVD and you use a Silicon gas SiH4 to do that, right. Silicon gas will be forming and forms a small crystal and they form polysilicon. So, polysilicon is basically sort of a silicon arranged in a special manner. So, they are crystal in small domain, but in a larger domain they are still amorphous in nature. So, they are heavily doped, you can heavily dope it to be a good conductor, right. So, polysilicon is used in that manner. So, now you have polysilicon, you have a thin gate oxide, then you have N well and then you have p type substrate. Now, you use the same lithographic process to pattern the polysilicon. So, what you do, use the polysilicon, you have an N well here, right, and then you pattern it to, say for example, you want to grow here and grow here, the same procedure which I discussed earlier, you can actually etch and remove the oxide layer and the polysilicon layer at these places where you have marked it, right, which we have already discussed in our previous section. An important point which is a current technology is that you require self aligned processes. Self aligned primarily means that if you have let us suppose you have a device which is something like this, that this is your N and this is your P, N plus and N plus, and this is your source and drain, right, and if this is overlap, so you are overlapping with it. Self aligned primarily means that you should have your oxide layer like this is the oxide layer, this is the oxide layer, and this self aligned means when the alignment of the oxide and the metal is exactly that with that of the source and drain material, and that is how you do it here. So, what you do is that you grow it like this, then use oxide and masking to expose N plus dopant should be diffuse or implant. Means now what we do is that we expose the polysilica and we try to, those places where we want the N plus dopant to go, we expose it, and for other reasons we stop it. Now, N diffusion forms NMOS device, of course, and if you want to have p type device, you will have p type diffusion, and therefore you will have N well contact, you will have source and drain available with you. We also use the N diffusion, as I discussed with you. These are actually self aligned processes where gate blocks the diffusion. So, gate will be typically polysilicon, you try to put your diffusion from outside and the gate will block it from going inside just below the gate. So, polysilicon is better than metal for self aligned gate because it does not melt during later processes, right. So, its melting point is typically very high for polysilicon as compared to even metal, right, and that is the reason you make it. So, this is the N plus diffusion, right. So, this will be N plus diffusion here and there will be N plus diffusion here as well as at here. So, this gate will not allow this diffusion to go inside this material, right. So, after you have actually diffused it with N type material, now you have an N plus region here, you have an N plus region here and you have an N plus region here already formed, right. Now, usually nowadays, initially we used to have diffusion, now use ion implantation to do it, but still historically they are known as diffusion. So, I have an N well here and I have diffusion. So, this is your diffusion, this is your diffusion and this is your diffusion generated region. Now, what you have done is, let me see what we have done. Therefore, now what you can do is you can strip off this layer of polysilicon, right. So, in the next slide you see, as I have removed this polysilicon by doing oxide layer. So, you remove the oxide layer and therefore, what we have done is all the oxide layer here has been removed. If you go back to your previous slide, this was the oxide layer which was there. Now, by doing HF etching or using some other technique, I can remove this oxide layer directly and I get almost devoid of any oxide layer in this case, right. If you want to do p type dopant, now since your N type dopant is finished, so I have an N MOSFET formation here, but I also want a p formation over the N well. So, what I do is that we exactly as we started with diffusion in N type MOSFET, we do diffusion using a p type material which is group 3 boron material, and we dope it with source and drain and substrate contact. So, what we do, source, this is the source, this is the drain, right, and you have a substrate contact which is this one. All these three can be done using the p well diffusion process. After I have done the p well, we need to have the final layer which is the metal layer, and to do that you require to grow a contact. So, what we do, we cover everything with a field oxide. Field oxide is a very thick oxide. So, this is the field oxide which you see, thick field oxide. These are very thick field oxide here, right, here. When you grow it, you do not allow any external species to enter anywhere else except the region which you have opened. Now, what you do, you cover it with thick field oxide and then etch oxide where contact cuts are needed. So, I etch it at this point, at this point, at this and this, right, and then you grow the contacts there. Once you have grown the contacts, which is this one, we have grown the contacts, we then sputter. After we have grown the thick oxide layer, now my region where you want to grow the oxide is open. Then what I do, I sputter with aluminum over the whole wafer. So, I do a sputtering using a sputtering technique. I sputter over whole aluminum. The aluminum actually sits at those places which was open, right, these were open spaces, and the metal fills in all these open spaces, right, and as a result what happens is that, sorry, as a result what happens in this case is that now you do have, now what you can do is, now you can remove this etched oxide here, right, and you will have a contact here, a contact here and a contact here. So, these two will be source drain contact for N MOSFET, this will be source drain contact for source drain contact P MOSFET. This is also known, this whole procedure is also known as twin tub process, right, because you grow a P substrate, you grow an N well within that, and then this is known as a twin tub process. With this I have given you a brief insight into the flow of fabrication in a silicon, and we will take up further issues than this as we move to the next slide. Thank you very much.